Hello everybody and welcome to my tutorial number 12 about Freecad CfdOf. In this tutorial I will show you how to simulate an explosive combustion with reacting foam. So on the left you see a picture taken from YouTube which shows um, an explosive combustion of methane, and on the right side you see the result of a simulation. So first of all, we have to calculate the necessary amounts of substance. We have a reaction from methane with oxygen, and the product is CO2 and 2 times water. So that means that we need 1 time mole of methane and 2 times oxygen uh, in order to have a substance which is in the right proportion. So now we have to take into consideration that, of course, we are talking about air. And this means that the ratio between oxygen and methane must be 2 to 1. And this gives the first restriction. This must be, so that means that we need 2 times more substance of oxygen compared to methane. The second restriction is that we are using air. The air consists of 23% oxygen, and so that means that the ratio between oxygen and nitrogen must be 23 divided by 77. With this, we can make a substitution of the first equation and go again into it. And if we transform this all together as one, this means that we will have an amount of oxygen of 0.206. The amount of methane is 0.103, and the amount of nitrogen is 0.691. This is a simulation model we will build up. So that means we have a closed room, but on the outside you see that is yellow. We need an outlet. The outlet is has a width of 10 millimeter and a deep of 5 millimeters. And in the middle you will see some kind of pillar. So with a diameter of 4 millimeter, this will get the temperature of 2000 Kelvin, and this will be the place where the reaction starts. Now let's build up the simulation model in Freecad. First, we start with the PartDesignWorkbench. We make a new file and go to the sketcher. We build up the sketch in the XY plane, and then we can start. So we use a polyline. We go 1 time to the right. Then I pressed 3 times the M key so that I get a radius. I go down. I press 3 times again the M key. I go to the left. I go a bit down. Go to the left. Go a bit up. Go to the left. Make a radius. Again with the 3 times M key. Go a little bit up. And I press 3 times M. And in this case, I will not close this. I will show you later on. So we finish this by clicking on the right button. So that's okay. So now we have to make the constraints. Of course, we start to close this. And we use this tangent restriction. So that looks good. So here we need a restriction that it is straight. I think here this should be also straight, and this should be straight. Now the points are straight. Then we will proceed making this symmetrically. Okay. Now these both are equal. Okay, these both are symmetrical. So now these both are equal. Okay, then we have to define the radius. The radius is 10. This radius will be 10. This radius is 10. And this radius is 10. Okay, it's not feasible to determine this. Probably this is also made by the other constraints, but this should be okay. So just ignore it. It seems that we don't have to fix this. So next thing what we will fix is we will enter here a distance of 10 millimeter. And the depth will be 5 millimeters. And these both points are symmetrical to the middle line. Now we can define the whole depth of this. The depth is this is the total length. This will be 50 millimeters. We can here define the length. The length is 30 millimeters. And now we've got, you see, everything is green, so the model is constrained, but we need some kind of pillar. So I start here. I draw this outside, but of course the middle point is part of this, is coincident with this line. And the distance will be 50 millimeters. And now we have to define the diameter. The diameter is 4 millimeters. And now we've got it. So we can close this. We can pad this up to whatever you like. This will be a two-dimensional model, so you can pad it up at whatever you want. So in this case, we take 10 millimeters. That looks okay. We can take a look from the side. Yeah, looks good. So we can, you should save this. Okay, now it's saved. Now our model is totally built up. And so we can go to the model again. The next step is to build up the CfdOf model. So first we must insert an analysis container. We do so. Then we can take a look on the different steps. So first we define the physics model. We will make this a transient model. Single phase incompressible is okay. The turbulence behavior will be laminar. That's okay. We don't need a gravity. That's everything is okay. So next thing is the fluid properties. That's air. We will exchange that later on, but for the first step, air is okay. For the field, we can for the velocity we should define 0, and for the pressure we can say this is 1E5. So this will be 100 kilopascal. That's okay. But later on, when we use reacting foam, we have to change this, but this is only the start value. But this looks okay. In the next step, we have to define the boundary conditions. So here we take this pillar and define this as a velocity. We say this is translating, but this is only to mark this later on. So here we say we have a velocity of 0.1, but this is only a dummy value. This is only that later on we will find this in the file. So we click on OK, and we will rename this wall to Spark. So here the label will be exchanged to Spark. That's okay. And the next boundary condition that we need is this one. This will be the blow off or the outlet. So we define again. We say this is this is just open, so that's okay. And we can define here a pressure of 1E5, but later on we will have to edit this again, but that's okay. We click on OK. So now the boundary conditions are defined. To make it more easy, we will rename this one here. We have the label open. We will rename this to outlet. This is just because in the file that we will use, we have already a label outlet, and so that means that we do not have to exchange this label. So this looks good. And now the next step is to define the mesh. We mark the pad and say make a CFD mesh. The base element size will be 1.5 millimeters. The mesh utility CF mesh, that's okay. And for this we need a mesh refinement because we have a two-dimensional model. So that means that we have to go to extrusion to the planar mesh thickness 1 millimeter, whatever you like. This has no influence. We can click on the front side, add this, and click on OK. So now that looks good. We can take a look. Yes, we can go again to the measure, make a double click on it, and say write the mesh case. That's okay. And now we can let the measure run. This will take about 40 seconds, so see you in 40 seconds. So now the measure has completed. We can review the mesh. We can say load surface mesh. So this is a very rough mesh. I must say that I tested this also with other meshes, and the simulation I will show you, this is very sensitive, and sometimes it works, sometimes it does not work. So with this rough mesh, it works, but when you take a mesh with more refinements, with if you take a mesh which is has a a smaller base element size, then probably you'll get some problems. Later on, I will show you how to solve these problems. Okay, now we have the mesh, we have the boundary condition, and we can go to the solver. So the first thing that we should do is this will be a very fast transient simulation. So the transient right interval, we will change this from 0.1 to 0. Um, to 0.001. But later on, I will show you that this is even not enough. Um, we will we must edit this in the files. So the next step is the similar end time normally is 1 second, but we will change this to 0.5. I will now explain how to change the setup of a simulation in reactingFoam. So I've already explained this in tutorial number 11, so this is just a repetition. So first what you must do is download the tutorial files from GitHub. Then you must change PimpleFoam to reactingFoam in the files allrun and in the file control-dict. You must also exchange the FE schemes and the FE solutions with the files from the tutorials. In the file in the directory constant, you must also eliminate all the files and then copy them from the tutorial files. You must copy the files alpha t and so on from the tutorials files into the directory case 0. For the pressure, you must change the dimension in the file p. For the pressure in the internal field p, you must change this to 1E5, and then you must adapt the patches in all files in all files to the patches of the model, and then you can start the simulation in Freecad CfdOf. So let's do so. So we make a double click on the CFD solver. We write the case. So now the case file has been written. We can click on the edit button. So first what we must do is go to the file allrun. We must edit this. So here you see that we must exchange PimpleFoam by reactingFoam. So we close the file allrun. We go to the system directory, edit the file control-dict, and here application we must exchange PimpleFoam by reactingFoam. And we can also delete the libs and the functions, because in this case they are not needed. We should make the write interval a bit smaller. So here we make it 0.005. So now everything has been changed. We can save this file. Next thing is we must delete the files FE schemes and FE solution. So that's okay. We go to the so these are the files taken from the tutorials. We just make copy and paste. So we insert them into the file case. So that's okay. And next step, we go to the directory constant. We delete all files that are here. But of course, the directory polymesh, we should let it. So here we go to the directory constant and we copy all these files into the directory of the case. So now that's finished. And what we must take a look on is are the thermophysical properties. You see that they are only defined in a range between 200 Kelvin and 5000 Kelvin. So in case you have higher temperatures, then you must edit these properties and you must adapt them. But this is very complicated, but in the Freecad forum, you will find a way how to do this. So in my example, we will not achieve higher temperatures, but in case you do so or you have problems, you have to change this. But in this case, it's okay. We don't have to change it. We close. And now let's go to the file 0. We have two properties, pressure and velocity. And here we can go again to the tutorial files and copy the all files um, except the pressure and the velocity files. We make a copy, we insert this. So the next thing what we have to do is change the pressure file in this. We edit this with an editor. Okay. So first what we must change are the dimensions, because these are the dimension for reacting foam and these are the dimension from PimpleFoam. Okay, that's okay. And the pressure itself is 1E5. That's okay. And also for the outlet, this should be 1E5. So that looks good. The other things we have default phase and so on. We don't have to edit this, so this is okay. So next thing, we go to the velocity file. All we have to do is here you find for the spark we have a velocity of 0. But we exchange this to 0. This is just to have this label spark, and yeah. So we can close this again, and this is finished. So next file is the temperature. This is taken from the tutorial. So we have to make more adaptations. And here we have already an outlet. And but what we don't have are the default phases. We have to make a copy from this. So this will be 0 gradient. That's okay. And the label air does not exist. The label fuel, we can here say this is a spark. And here we will have a temperature of 2000. And the temperature of the internal field is just 293 degrees. So now our file temperature is okay. We can close this. We can go to the other files. So we go to Y default, to Y default, and to alpha T. We can edit this. So the first thing is we remove the label air and replace this one fuel by spark. The outlet is okay. There's one label missing, and that's the default faces. We go again to the Y default. So now we have defined the default faces, but we should edit these values. So here we have, yeah. So this is already okay. We can go to the alpha T. We insert also the default faces. No, sorry, was wrong. We go to the pressure, copy this, go to alpha T. So now we have the label default faces, and we can copy this one. We remove the label air, and this one will become spark. Now I've just seen that no, we should insert everywhere zero gradient. That's sorry. It has not a large influence, but we in this case we should say that it is everywhere zero gradient. That's better. So we can save these files. And now we can go to the substances. We go to the oxygen, nitrogen, water, CO2, and methane. We added them with a notepad. So first what we do is remove the label air, and this one will become spark. We do this for all the substances. Remove again the label air, insert the label spark. So you see there's a lot of work to do, but yeah, that's so. We insert spark. Now the next label that is missing are the default faces, so we have to copy them. We insert them to the nitrogen, to the methane, and to the water file. The type zero gradient, that's also the type for the spark. So again, we insert everywhere for the spark a zero gradient. So here we have also okay, that looks good. So now the CO2 file is already has been finished. We don't have to change anything. For the nitrogen file, yes, here we have to edit a lot of things. So first, for the internal field, the value 1 will be replaced by 0.691. So this is the amount we have calculated in advance. And for the outlet, this will be normal air. So here we have a portion of 77%, and we input this. Okay, that looks good. For the methane, the outlet is 0, that's okay, but the internal field, this will be 0.103, that's okay. So next file we will take a look on is the oxygen. For the internal field, we will have an amount of 0.2606. And on the outlet, we have normal air. That means we have an amount of 0.23, that's okay. And here also 0.3, that's okay. And for water, the internal field is 0, that's okay. And the outlet, that's also okay. So now if we've made everything right, then we can run this. So we've saved our files. And we can close this. So now our simulation should be completed, and we can start the simulation. And this simulation will run about 5 minutes, 10 minutes. So see you in 5 or 10 minutes. The simulation has finished. The calculating time was 3 minutes and 4 seconds. We click on ParaView in order to review the results. So we go to the first time step. And the first thing that we take a look on is the temperature. So you see that we have a range of 200, 290 degrees up to 2000 degrees. So that looks good. This is the first simulation. We let it run, but be aware that it should be stopped after a while. Yes. So you see that this simulation is very, very fast. So you see that after 0.04 seconds, everything is done. So we step again back. And this is the time step before. So here we have an area where we have a cold air. This is a mixture between methane and air. And here we see the front of combustion. And this is where we should take a deeper look on. So first what we can see is um, the generated heat. This is Q dot. And here you see this is the area where the heat is generated. We take a look on CO2, on the carbon dioxide. You see that we have here around this pillar, we have an area where we have a high concentration of carbon dioxide. Around there is no carbon dioxide. So next thing what we can take is the water. That's similar. On the other hand, here we see that um, the concentration of methane is 0.1. This is what we have defined. And around this pillar, so this is the area where the combustion took place. So we nearly don't have any carbon dioxide left. So we go one step further. And here you see that nearly everything of the carbon is erased. And so here the simulation has already finished. So the combustion has finished, and there was a movement of air and methane outside this body, and now we have a flow back. We can take a look on this flow back. We can take a look on the velocities, and we can take a look on the direction y. So here you see that we have something stepping back. This is but if we go one step further, you see that we have a high velocity of blowing out of the substances. Here it is minus 20 meter per second, and here we have also a high velocity blowing out. We can take a look on the magnitude. So you see that the magnitude is concentrated in this area. Let's come to the conclusions. So first conclusion is the explosion of gaseous substances can be simulated with reacting foam. In this example, the substances methane and air were used. In this simulation, a blow-off was used in order to keep the simulation stable. Tests with closed rooms were not successful. The simulation is not very stable. Many tests have failed. I must say this in advance. I've made a lot of tests, and so normally the simulation was aborted. And yes, so this example that I show you, this ran, but this is not very. So you can improve this, but probably this will not be stable, and so on. And the last point is that thermophysical properties for the substances are only defined up to 5000 Kelvin. In some tests, this temperature was exceeded and the simulation aborted. This error can be seen in the file log point reacting foam. In case higher temperatures should be considered, the file thermo.compressible gas must be edited. Thank you very much for your attention. I hope to see you in the next tutorial. My next tutorial file will be about the Kelvin-Helmholtz physics. And yes, I hope to see you in the next tutorial. Bye bye.